Hello all and thank you for taking the time to watch this video. I hope your day has been great so far and that you may find this video both informative and enjoyable to watch. In this video, I will be briefing you on how to set up and prepare the Albatross aircraft for flight using a number of simulated flight dynamics assessments. The software Unity will be utilized to perform all flight dynamics simulations in order to properly prepare and set up the aircraft and to ensure its flight worthiness. Before starting the brief, a few assumptions have been made regarding the Albatross. The aircraft weight is fixed at 7 kilograms, and the neutral point of the aircraft is located at approximately 50% of the mean aerodynamic chord. The maximum static engine thrust is 30 newtons, and the maximum control deflection is limited to plus minus 25 degrees. Lastly, the default CG position for flight testing is assumed to be at 35% of mean aerodynamic chord. The very first test that we will be doing is the weight and balance test. The aim of this test is to verify the overall mass of the aircraft as well as the CG location of the aircraft using real reaction measurements for a range of different CG locations. The black and white sphere shown here represents the center of gravity, and the blue bar represents the mean aerodynamic chord. The front of the blue bar represents the leading edge of the mean aerodynamic chord, which also acts as the reference coordinate frame for the CG and the wheel of the Albatross, with Z acting as the longitudinal variable. Z is positive aft of this point and negative forward of this point. As you can see, the Z value for the CG location in its current location is 0. As I increase the Z value to a more positive value, such as 0.1, it moves aft and away from the leading edge of the mean aerodynamic chord. The opposite will happen as I change the value to a negative value. As I change the Z value of the CG locations to negative 0.1, it now moves forward of the leading edge of the mean aerodynamic chord. As you can see, the Albatross's landing gears are placed on top of a weighing scale, showing the mass reaction on each scale. Since we know the position of the landing gears relative to the Albatross, and that we now know the force in each landing gear, we can calculate the moment arm on each landing gear and subsequently estimate the location of the center of gravity, which differs from the Z value CG location in the simulation. As we change the Z value of the location for the CG, the forces in each landing gear changes, as can be seen here. If I were to change it from right at the leading edge of the mean aerodynamic chord to 0.1 meters aft of the leading edge to the mean aerodynamic chord. The longitudinal location of the test CG has been incrementally varied in order to determine the total load. Multiplying the moment arm by the measured load gives the moment, and the total moment can be calculated by the total load to estimate the CG location. The estimated value is then plotted against the experimental test value and in theory should yield a y equals x relationship passing through the origin. There is a slight discrepancy between the estimated and the test values, however, this is not too significant. Additionally, it is also very important to consider the CG longitudinal limits, as going past certain Z values induces a tipping moment on either the nose or the tail of the Albatross. In this case, the location of the CG should not exceed past 0.34 meters forward of the mean aerodynamic chord leading edge and 0.15 meters aft of the leading edge of the mean aerodynamic chord. Setting the location of the CG to 0.35 meters forward of the reference point induces a nose tipping moment, and setting the location to 0.15 meters aft of the reference point induces a tail tipping moment. As you can see here, if I were to set the Z value for the location of the CG to 0.16, which means the location of the CG is now 0.16 meters aft of the leading edge of the mean aerodynamic chord, a tail tipping moment would be induced. The second test is the thrust measurement test. Located at the nose of the Albatross is a force sensor which will read the thrust produced by the Albatross relative to the RPM input, which can be seen on the top left of the flight instrument display. The static thrust may be determined at CG location of 0.05 aft of the leading edge of the mean aerodynamic chord. At maximum RPM, the thrust imposed on the sensor by the Albatross is 28 newtons. Let's observe. There you go, 28 newtons at 100% RPM. For this test, Multiple incremental RPMs and their corresponding thrust has been measured, and a graph of RPM against thrust measured is plotted, as can be seen. This gives the user an idea of the static thrust and their variation for different RPM values. The third test is the static control test. The aim for this test is to set the flight control configuration of the Albatross. The initial configuration for the flight control surface was simply incorrect. The configuration has therefore been corrected to the configuration shown on the screen, including the roll, pitch, yaw, throttle, and flaps configuration. The correct flight control configuration is therefore as demonstrated. Roll left, roll right, flaps down, pitch up, and pitch down. The next test is the longitudinal dynamic response to controls test. The trim induced by the elevator is controlled by the page up and the page down keys on the keyboard. The wind speed has been increased in this test to allow for a more realistic condition. In order to gauge the flight performance of the Albatross, a wind tunnel test was conducted. The performance of the aircraft was tested in the wind tunnel by varying the angle of attack while setting the CG location, flap configuration, and elevator deflection angle. As can be seen here, this is the experiment that is taking place in order to gauge the flight performance of the Albatross in the wind tunnel. The data for the static wind tunnel tests were recorded in Excel. Looking at the plot for lift coefficient against the angle of attack for three different flap configurations of 0, 20, and 40, the CLmax for each configuration is noted. It can be observed from the plot that there is an increase in CLmax as the flap configuration increases from 0 flap deflection for the blue line all the way up to 40 flap deflection on the grey line. The CLmax for all flap configuration occurs at 14.83 degrees. The official Albatross datasheet suggested a maximum angle of attack of only 12.83 degrees, which shows a discrepancy of 2 degrees between the maximum angle of attack shown in the datasheet and the maximum angle of attack retrieved from the simulation. This could be due to factors such as inaccuracies in the Albatross's aerodynamic characteristics in the simulation, such as possible slight differences in wing shape and airfoil design, or other simulation errors such as control surface limitations, and others. The Albatross datasheet also mentions the CLmax at both flap 0 and flap 40 settings. The CLmax for cruise when the flap is set to 0 is 1.2, and for when the flap is set to 40 is 1.4. The next graph shows the lift coefficient against drag coefficient for flap configurations of 0, 20, and 40. Stall behavior may be observed from the graph for all configurations, for all flap configurations, once the CLmax has been exceeded. The CLmax may be a negative value, but the CD must always be non-negative as drag is always acting in the opposite direction of motion. This graph shows the moment coefficient versus lift coefficient plot for three different elevator configurations, -15, 0, and 15 degrees. The closest line to passing the origin is the blue line, when the elevator angle is 0 degrees. For reference, the CG is located at approximately 35% of the mean aerodynamic chord. The coefficient of moment for 0 degrees elevator angle for when the CL is 0 is 0.1, which is close to 0. Therefore, an elevator trim of 0 degrees is the most ideal for maximum trim performance in this scenario, with the CG located at approximately 35% of the mean aerodynamic chord. Lastly, we have the CM at different CG locations against the CL plot. This plot represents the longitudinal stability of the Albatross, and ideally, for a stable aircraft, the plot should be negative, as a positive plot suggests instability. As you can see from the plot, the dark blue line is the most negative plot on the graph. This is for when the CG is approximately 0.05 meters forward of the leading edge of the mean aerodynamic chord. The last step for the preparation of the Albatross to ensure its flight worthiness is performing a free flight test. For ground maneuverability, the rudder and nose gear steering for the Albatross provides sufficient ground maneuverability at low speed. However, at higher ground speed, the risk of wing tips strike with the ground increases, and the increase in lateral force due on the nose gear could also cause nose gear failure. The minimum takeoff speed without flaps is about 18 meters per second from 0. And with flaps open, this speed becomes 17 meters per second. As you can see, the Albatross has reached cruise flight, steady state flying conditions, and this was achieved at an RPM of 73% and a speed of 54 meters per second. Thank you very much for watching this video. I hope you found this video useful, informative and enjoyable to watch, and I hope it gave you an insight on how to set up the Albatross aircraft.